Okay, so in this video, we're going to essentially cover section 32, and we're going to introduce the Riemann integral. We're actually going to talk about just some basic definitions, and then we're going to give the definition of Darboux integrals. So as you can see here, we are going to give the definition of two integrals, the Darboux integral and then the Riemann integral. Then the next thing we're going to do is to discuss the connection between Darboux integrability and Riemann integrability. Spoiler alert, they are the same. So if a function is Riemann integrable, then it is Darboux integrable and vice versa. Okay, and then this last section here, I'll probably do in a different video. This is for section 33, properties of Riemann integrable functions. And remember, Riemann integrable is the same thing as Darboux integrable. Okay, so let's get started. And to get started, we need to have some definitions. So everything that we're doing in this section is assuming that f is a bounded function defined on the closed interval AB. Let me actually highlight this, because everything that we are doing, the definition that we are giving, these definitions are assuming that f is bounded, and they're assuming that the domain of f is a closed interval, that closed and compact, right? That closed and compact interval AB. Okay, so the first definition we have is that of a partition. Now, we have here some notation, big M and little m. Okay, so big M is essentially the supremum of the function on the set S, and little m is the infimum of the function on that set S. So always we have that for little m of SS is going to be less than or equal to big M of F on S. Okay, and that is true for any F and for any S. So let's be specific. So for all F and for all sets S, S is a subset of the domain of F. Okay. Now, so our first definition here is going to be that of a partition. So a partition of this domain AB is a subset. And basically what you're doing is you are taking your domain AB and you are parting it. So you're creating these little subsets, sub-intervals, essentially. So let's just show you how that looks. So for instance, if you have here's A and here's B, you can have a partition P with, you can take your interval and create in little parts. So remember, your partition is actually a subset of AB, and the key is that T naught needs to be equal to A, and T sub n needs to be equal to B, and then you can have T1 anywhere you want, T2 anywhere you want, T3 could be close to T2, then maybe T4 is here, dot, dot, dot. Okay, so you need for TK to be less than or equal to TK plus 1, right? And this needs to be true for all K equal to 0, 1, all the way up to n minus 1. Okay, so you need to have that true, so an increasing set of points, strictly increasing. Then you need to make sure that your first point is A, and your last point in your partition is B. Okay, and that's what we mean by a partition. So this is basically what we're doing is we're taking this interval AB, and we are creating subintervals. So like here's our first subinterval, now here's a second subinterval. We're creating subintervals, and we're going to do our analysis on these subintervals and let the choice of subintervals vary. Okay, so that's a partition. Now we come to the formula for an upper Darbo sum. An upper Darbo sum, which, so the U here stands for the fact that it's upper, and this is compared to a lower Darbo sum, which has a big L, okay? And it is of the function f with respect to the partition P. So here's what we do. In order to create these upper sums, our upper Darbo sum and lower Darbo sum, basically what you're going to do is you have this formula here, which is you take the supremum. So remember, this is the supremum, that big M is the supremum of f on this subinterval, tk minus 1 to tk, times the length of that subinterval. Okay, so this is the length of the subinterval. And this is the sup of the function on that subinterval. And similarly, the lower Darbo sum is the nth of the function on the subinterval times the length of the subinterval. And you do that for each interval, and then you add them all up, and that gives you your Darbo sum. Okay, so let's look at an example of a partition, an upper Darbo sum, and a lower Darbo sum. Let me just check to see what did I have. Okay. So the first example that we'll do is, suppose we have, so here's our example, is going to be our function f of x equals x squared. Okay, and we want our, so we've got our function f, we need a partition, and we need a partition of a domain. So we'll say that AB, let's say this is equal to some interval 0 to b. Okay, and the first thing we might want to do is we might want to consider the partition P to be equal to 0, and then maybe b over 3, 2b over 3, and b. Okay, so now, so here's 0, and here's b. I have an idea. I know what, actually I think I can draw this a little better. I want to compute the upper Darbo sum of f with respect to this partition and the lower Darbo sum. Okay, so in order to do that, let us so we're going to graph here. Now I know the function of this is going to be y equals f of x, and here's x. So say here's 0, and here's b. Okay, now my partition is 0, b over 3, 2b over 3, and then b. So that's my partition. So first thing I'm going to compute is the upper Darbo sum is going to be equal to, I need to take the supremum of f over the interval from 0 to b over 3 times, so this is b over 3 and this is 2b over 3. times the distance, right? So if this is t, this is tk, and this is tk minus 1, and this is t sub k. So I need my delta t, which is tk minus tk minus 1, right? So for me, that's going to be b over 3. So I have b over 3. And I'm going to do this for each subinterval, okay? So plus the sup of f. This time I'm going to have from b over 3 to 2b over 3 times b over 3, because that's the length of the subinterval. And then plus, let's see, over here I'll have the sup of f over 2b over 3 to b, okay, times b over 3. And when I add it up, let's go up here. So my UFP is going to equal, now what is the supremum of f over this interval? So over this subinterval, the supremum is going to be b over 3 squared, okay? So this is going to be b over 3 squared.
1815.
What is the supremum over the next interval? So the sup of f over the second subinterval is going to occur, is going to be, I need 2b over 3 squared. So 2b over 3 squared. And then for the last one, for the last subinterval, the supremum is going to be, just b squared. Okay, so my upper Darbo sum is going to equal b over 3 squared times b over 3 plus 2b over 3 squared times b over 3 plus b squared times b over 3, which is equal to, and we could actually pull out b over 3. So we'll have b squared over 9 plus 4b squared over 9 plus 9b squared over 9. So that'd be 9, 10, 14, 14b cubed over 27. Okay. This is 14b cubed over 27. And now let us compute the lower Darbo sum. So to compute the lower Darbo sum, the only thing I'm going to do is, instead of looking at the sup, I'm going to look at the inf. So I'm going to compute the infimum over these same subintervals. Okay, so let's put in here. So my lower Darbo sum is going to be the infimum, infimum, infimum. Okay. Now, on this first subinterval, the infimum, what's the smallest value of f, is going to be 0. What about on the second subinterval? The infimum is going to be b over 3 squared. And then on the third one, the third interval, the infimum is this value right here, which is going to be 2b over 3 quantity squared. 2b over 3 squared. Okay, so now if I'm computing my lower, so I can actually just erase this and this. Oh crap, I was not supposed to do that, because I'll forget what that was. Okay, so that's the upper. Let's just erase here for the lower. So we'll say that's the upper. Is equal to that. Now for my lower Darbo sum, I should get 0 times b over 3 plus b over 3 squared times b over 3 plus 2b over 3 squared times b over 3, which would be equal to b over 3 times, this would be 0, plus b squared over 9 plus 4b squared over 9, which is going to be 5b cubed over 27. Okay. So that's my lower. And then for the upper, we've got the upper Darbo sum there. So notice that these Darbo sums depend on, of course, they depend on your choice of f, right? So if you change the function, that's going to change the sum. But more importantly, they depend on the choice of partition. Okay, so if you change your partition, then you very well may get a different sum. Okay, and it should be clear from the definition. It should be clear from the definition of the upper and the lower Darbo sum that you always have, for any partition, for any p, the upper Darbo sum is always bigger than or equal to the lower Darbo sum of that p. Okay, so let me in fact write that down. So for all p, if you fix p, the upper Darbo sum with respect to that partition is always bigger than or equal to the lower Darbo sum, right? Because if we compare this formula to this formula, right, this sum on top will have terms that are always, the soup over this set is always going to be bigger than or equal to the nth. So these sums, the upper sums, are going to be at least as big as the lower sums. Okay. So that gives us that leads us to our first fact, which is that, again, we're assuming the f is a bounded function on this closed compact interval AB. The fact is, for any f, so for any function f, and for any partition P, m times b minus a is less than or equal to the lower sum, less than or equal to the upper Darbo sum, and the upper Darbo sum is less than or equal to big M. Now here, just for clarity, so here, m is equal to the infimum of f of x over all x in a and b. And big M is the supremum of the set f of x, where a is in between x and b. So since f is bounded, since we're only dealing with bounded functions, we know that m and m have to be finite real numbers. Okay, so now how do we get that? Well, let's look. So we already talked about the first, so we talked, if this is our first inequality, right? So if our first inequality is this, and then our second inequality, I guess, would be in the middle. Second inequality would be to say that lower sum is less than or equal to the upper sum. We already proved number 2. And then the third inequality states that the upper sum, our upper Darbo sum, is less than or equal to big M times b minus a. So let's just look in detail at the, well, we can look at number 3 first. Okay. So looking at number 3, we'll notice that UFP, so we'll say fix a partition P. Well, this is, I'm going to run out of space. Let me. Here we go. Okay. So let's see. So this is for number 3. So hypothesis is that F goes from AB to R. F is bounded. Also P is a partition of AB. Claim is that this upper Darbo sum of F with respect to P is less than or equal to m times b minus a. And so for the proof, here's what we'll do. So we'll say we know that the upper Darbo sum is equal to the sum. Okay, so in order for me to do this formula, I need to have some notation for my partition P. So let's put in here in the hypothesis that P is equal to the set of T naught, T1, all the way up to T sub n. Okay, so now in my definition, I can put that this upper sum is equal to the supremum of f of x such that x is in between t sub k and t sub k plus 1 times, so does this number, times t sub k plus 1 minus t sub k. And I need to add up, so I need to multiply those numbers together and then add them up. I need to do it for k starting at 0 and stopping at n minus 1. Okay. But we'll say that notice that for each k equal to 0, 1, all the way up to n minus 1, the supremum of the set of f of x, where x is in between t sub k plus 1 and t sub k, this supremum is going to be less than or equal to m, because m is a supremum of f of x, where x is in between a and b. Right? So if we consider a larger set, then the supremum can only go up. The supremum is greater than or equal to. If we were considering a smaller set, right, a subset, the infimum can only go, let's say the supremum can only decrease if you're looking at a smaller set. Looking at a larger set, the supremum can only increase. Okay, so if you're looking at, yeah, okay. All right, so now why is this important? Why do we care? Why do we care? Aha, because if this is true, then that means that our upper sum is less than or equal to the sum of m times tk plus 1 minus t sub k. K equals 0 to n minus 1. And notice that this is the same as this m is a constant, so we can pull it out. So we'll say this is equal to m times the sum, k equals 0 to n minus 1, of t sub k plus 1 minus t sub k. And this sum is just equal to b minus a. Okay, so now why is that true? Well, let's see. So this is T1, T sub 1 minus T naught, plus T sub 2 minus T1, plus dot dot dot, plus T sub n minus T sub n minus 1. So it's a telescoping sum. So right, so it's T sub 1 minus T naught, plus T sub 2 minus T1, plus T sub 3 minus T2, plus dot dot dot, plus T sub n minus T sub n minus 1. Right, and then this T1 is going to cancel out with that negative T1, minus T2 is going to cancel out with T2, right? The T3 is going to cancel out. So everything is going to cancel out except for T sub n and negative T naught. But T sub n has to be equal to B. T naught has to equal A. So you get B minus A. Okay. So this is the proof of number 3. And the proof of number 1 is very similar. So if we wanted to prove 1, let's see here. We would show, we want to say that little m times b minus a is less than or equal to the lower Darbo sum. And we could just change this to infimum, right? So the lower is equal to the infimum of those sets, and the infimum of that is bigger than or equal to little m, which is the infimum of f over the entire domain AB. So then we get that the lower sum is bigger than or equal to this sum. And now we can change this out, bring that constant out front, and use the fact that it's telescoping. Thank you. To get the desired result. Okay. So now let's talk a little bit about, or let's give some more definitions. We've got 2 more definitions. The upper Darbo integral of f is the infimum of all of the upper Darbo sums. So let me show you just a picture here of what's going on. So if this is your upper Darbo integral, then all of your different upper Darbo sums have to be bigger than u of f. Right, so these are all different possibilities of upper Darbo sums. Okay, and similarly, the lower Darbo integral is the supremum of all of the lower Darbo sums. Okay, so notice that the lower Darbo integral doesn't have any mention of a specific partition because it is the soup. It's the biggest possible lower, in some sense, the biggest possible lower Darbo sum. So if we have our lower Darbo integral here, then behind it will be all these different possible choices of lower Darbo sums. Okay, and you've got to have sums. It's the supremum, right? So that means you've got to have lower sums arbitrarily close to that lower integral. Okay, now we are ready to define our integral. So we say a function is Darbo integrable if the lower integral is equal to the upper integral. Okay, so if the lower integral is equal to the upper integral, then we use this notation here. And it is equal to that lower integral, which is the same as that upper integral. So these should kind of remind you of limits. Again, remember the completeness axiom lies beneath almost all that we do in this course. So if we've got that soup, if the soup of the lower sums is equal to the nth of the upper sums, that function is Darbo integrable. And its integral is the same as the lower sum and the upper sum. Okay, let's look at 2 examples. Example number 1 is f of x equals x squared on the closed interval zb, 0 to b. So we're going to look at this, and we want to, the question is the function Darbo integrable on AB? That's the question. So in order to check that it is, or in order to determine this, we need to look at the lower integral and the upper integrals, and verify that those are equal to each other. Okay, so how are we going to look at, what about the lower? So let's see. So let's work on this first one here, which is f of x equals x squared, and it's on the closed interval from 0 to b. Okay. So now I know that I want to say is the upper integral equal to the lower integral. That's my question. Now, the upper integral is equal to the infimum of the set of upper sums. So P is a partition of A 0 to B. Okay. Now, a typical upper Darbo sum is equal to, what would we have here? Well, it would look like this. It's going to be the sum. Now, if I have a partition, so say I have a partition, my P looks like T naught, T1, all the way up to T sub n. I know, because of my function being f of x equals x squared, I know that the sup, right? So the sup of f on any subpartition, any part, that is always going to be T sub k plus 1 squared, right? So I know that just because I know that my function x squared is always increasing. So here I need to put T sub k plus 1 squared times, now the length of that subinterval is going to be T sub k plus 1 minus T sub k. Okay, and this will have k starting at 0 and stopping at n minus 1. So this is a typical upper Darbo sum. Now, we can look at the specific case of just taking the specific partition of just taking our interval and dividing it into n subintervals of equal length. So I'll have 0, b over n, 2b over n, 3b over n, all the way up to just b. You see what we're doing here? So we're just taking that domain from 0 to b and splitting it up evenly into n different subintervals. Okay, so for that partition, I can compute my upper integral, my upper Darbo sum, is going to be equal to, well, now I know this is going to be, the k plus 1 is going to be, it'll just be k plus 1 times b over n, right? So we can have k plus 1 times b over n, all of that squared. So that is my sup. Now the distance, what is the length of these intervals, right? The length of each interval is going to be b over n, right? Because that's the whole point, is the whole length of the interval is b, and I'm taking b and I'm dividing it into n subintervals that have the same length, okay? So here I'm just going to put b over n, and this is going to be from k equals 0 to n minus 1, So then I get the sum from k equals 0 to n minus 1. Now I'll have k plus 1 quantity squared times b cubed over n cubed. B cubed over n cubed is a constant with respect to k, so I can bring it out front. And I have b cubed over n cubed times the sum, k equals 0 to n minus 1, of k plus 1 quantity squared. And then I think it was on some homework assignment or something like that, or maybe it was on an exam, something like that. So we know that by induction, that the sum of k squared from k equals 1 to n is equal to n times n plus 1 times 2n plus 1 over 6. Okay, so we know that. So here, if I reorder this, so let's see here, so just let j equal k plus 1, and then k equals 0 if and only if j equals 1, k equals n minus 1 if and only if j equals n, and I've got j squared here. So this should be equal to n times n plus 1 times 2n plus 1 all over 6. To n plus 1 all over 6. Excuse me. Sorry. Okay. So I'll have, what is this? Looks like, so I have b cubed over 6 times n over n times n plus 1 over n times 2n plus 1 over n. Okay. So what does this mean for us? Well, u of f is the infimum, right? So that means that u of f has to be less than or equal to this number here. Now remember, we did this for any n, but u of f is the infimum of over all partitions. So let me add a page after, add a page below. So we'll say this. So for any n, u of f has to be less than or equal to u of fp, right? Now this is the partition of AB into n equal subintervals, or n subintervals of equal length. So for all n, u of f has to be less than or equal to b cubed over, what was it, 6 times n over n times n plus 1 over n times 2n plus 1 over 6 n. So, oh yeah, okay. So if for all n, u of f has to be less than or equal to this on the right-hand side, so u of f is less than or equal to, so we could do this, b cubed over 3 times n plus 1 over n times 2n plus 1 over 2n. If this is true for all n, that means that u of f has to be less than or equal to, because that's going to 1, that's going to 1 as n goes to infinity, be less than b cubed over 3. Okay. Now, here's what we'll do. So we've got an upper bound on u of f. Now, similarly, we can consider the lower Darboux integral, right? And we'll say that for each n, consider P sub n is going to be the same partition, 0, b over n, 2b over n, dot, 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 all the way up to b. Then the lower Darbo Sum with respect to that partition is going to be equal to the sum. Now remember, okay, so we need the infimum, and this time for the infimum, what will we get? We will get, so after we work it all out, we'll get k equals 1 to n, k minus 1 squared times b squared over n squared. All of that times b over n. Right, because remember, we want this infimum. So instead of taking the value of f at the right endpoint, we're going to take the value of f at the left endpoint to get that infimum. Okay, and so this is now going to give us b cubed over n cubed times n minus 1 times n times 2n minus 1 over 6. This, of course, right? So for all n, our lower sum is bigger than or equal to b cubed over n cubed times n minus 1 and 2n minus 1 over 6.
It's 1845.
Thank you. We can rewrite this. Let's see here. So put the 6 here and the n cubed here. So put n cubed here and put 6. Actually, let's put 3 and 2n cubed. And so now this clearly is going to go to 1. So L of f is bigger than or equal to b cubed over 3. All right. So we have that L of f and L of f is going to equal U of f, which is going to equal b cubed over 3. Because remember, that L is our supremum of our lower partitions and U is our infimum of our upper partitions. So it's okay for us to write the integral from 0 to b of x squared dx is equal to b cubed over 3. Okay. Now, let's look at another example. The other example is the characteristic function of the rationals on the closed interval 0, 1. So what is this? What is the characteristic function of the rationals? Well, this is the function that we talked about in class the other day, where the value on x is equal to 1 if x is rational and 0 if x is irrational. Okay, so now here, let's look and we'll look and see, let's look at those lower and upper sums. So we'll just say, notice that for any partition P of 0, 1, the supremum of our characteristic function of x, this is x in between tk plus 1 and tk, this supremum is going to equal 1, and the infimum is going to equal 0. Why? Because every subinterval contains rational numbers and irrational numbers. Okay, so that means that for any partition, the upper Darbo sum is going to be equal to the sum of 1 times tk plus 1 minus tk, right? K equal 0 to n minus 1. And that's just going to end up being b minus a, which is 1 minus 0, which is 1. And the lower sum is going to be equal to 0 times tk plus 1 minus tk, which is just going to be equal to 0. Okay, so add a page below. So u of f, which is equal to the infimum of the set of UFP, such that P is a partition of 0, 1, well, that's just equal to the infimum of the set 1, because this is always equal to 1, right? This is always equal to 1. So u of f, our upper Darboux integral, is equal to 1. And similarly, the lower Darboux integral, which is the supremum of what's going to be 0, right? Because we just showed that our lower Darboux sums are always equal to 0. So the supremum of the set of Darboux sums, lower Darboux sums, is going to be equal to 0. So since the lower Darboux integral is not equal to the upper Darboux integral, the characteristic function is not integrable. Darboux integrable. 1, 0, 1. Okay. All right, so let's see, I thought I had, oh yeah, okay, so before we get into Riemann sums, we're going to come back to Riemann sums, because remember, our whole goal is to talk about Darboux integral and Riemann integrals, right? So Darboux integrals and Riemann integrals. So first, let's talk about some properties of Darboux integrals. And then we'll come back to the definition of Riemann sum. Okay, so here's the first property. If f is bounded on a closed interval, because that is always our assumption. So the first fact we have is that if P and Q are partitions of A and B, and Q is a refinement of P, then we've got these 3 inequalities. Okay, so let's call this one the first inequality, this one the second inequality, this is the third inequality. So notice here, we're saying that Q is a refinement of P. Now, what does that mean to say that Q is a refinement of P? Well, that means that here's A, here's B. So say P has some points. So P is a partition of AB, but also P is contained in Q. So Q contains all of the points that P does, and Q contains more points. So let's put Q in this different color. And now Q is going to have everything that P has. So Q has all of the points that P has. Okay, but Q has more points. You get it? So Q is finer than P because Q is turning our interval AB into more subintervals, right? So it has all of the information that P does and more. Okay. So let's look at this first inequality, which is saying that the lower Darboux sum with respect to P has to be less than or equal to the lower Darboux sum with respect to Q. Okay, so this is our goal. So we want to show that the lower Darboux sum of F with respect to P is less than or equal to the lower Darboux sum of F with respect to Q, since P is in Q. Now, I'm going to just talk about why this is true, and for formal proof, I will refer you to Ross. So the formal proof involves induction, but we're just going to talk about the key reasons so we can understand really why this makes sense and why this is a believable statement. Okay, so on the one hand, this is going to be the sum, right? So the lower Darboux sum with respect to P is going to be a sum of this form. So it is the, so we want the infimum. It's going to be the infimum of set of f of x such that x is in between t sub k and t sub k plus 1, okay, times t sub k plus 1 minus t sub k. And this is going to be true for k equals 0 to n minus 1. Now notice that P and Q share, right? Q has all of the same T sub k's as P. So if we've got Q, so remember P is in blue, so P is in blue, and Q I think was in hot pink. Q is in hot pink. So here's what's going to happen. When we look at the lower sum for Q, it's going to be the sum of the infimum of f of x such that tk is less than or equal to x less than or equal to t sub k plus 1 times t sub k plus 1 minus t sub k. But now here's where things might be different. It's going to have all of the same, it'll have all the same points that P did. But now imagine you're in a situation like this interval here. Okay, so here P has this T sub k and this T sub k plus 1. But now Q has T sub k, and then let's call this, what if we were to call this T sub k plus a half? You get the idea, right? So Q is taking this interval and turning it into two subintervals, right? Now here's the idea. For the lower sum with respect to P, you'll have the sup of f of x over T sub k to T sub k plus 1. Sorry, the nth. But the infimum of f over this interval has to be bigger than or equal to the infimum of f over T sub k to T sub k plus a half, right? Times T sub k plus a half minus T sub k plus the infimum of f of x T sub k plus a half to T sub k plus 1 times T sub k plus 1 minus T sub k plus a half. T sub k plus 1 minus T sub k. So let me show you what I mean. So if I have some function, so here's my function f of x, and here's T sub k, and here's T sub k plus 1. If I'm looking for the infimum, right, the infimum over all of this, the infimum over this entire space, over this entire subinterval, times, so my infimum times that delta t, versus the infimum if I take this same subinterval and I split it up. Okay, so now I'm going to go over here, from here to here, and from here to here. Now I've got the infimum over my first subinterval, which it looks like that stays the same. But for my second subinterval, my infimum is actually higher. Do you see? So by taking a finer partition, I've made a better estimate. So my, let me see, I hope I did this right. I made a better estimate. So my infimums are going to be going can only increase. Does that make sense? So what I want to do is I'm going to say, so the infimum times f, the infimum of f times the delta t is going to be bigger than or equal to the infimum of f of x times the delta t over here. Right? Where here I've taken my delta t and split it into sub-regions. Okay, so I hope that makes sense. Pretty much the picture, the key picture is to see that if I'm looking at the infimum over the entire interval times the length of the interval, I will get a value that is smaller than looking at the infimum over the subintervals and adding those up. And so now remember, overall, what's happening is the Darbo integral is the supremum of all these sums, right? So if you have your lower sums, the higher your lower sum is, the closer it is to being the lower integral. Does that make sense? So like here, this would be LFP,
It's 19 hours.
and this would be LFQ, right? So we're saying if P is contained in Q, then LFQ is closer to L of F than LFP. Okay? So in some sense, L of F is overall, if you had to give one number to represent the integral, right, you're going to pick the biggest of the underestimates, right? Each lower Darbo sum is an underestimate, right? And so you want to pick the biggest underestimate. And we're saying that the finer your partition, the better your underestimate will be because it'll be bigger, okay? And it is very similar reasoning. So we already talked about number 2 before. We talked about number 2. Number 3 is very similar. Number 3 has very similar reasoning. So number 3 is true because if you, and let me just, here's the picture for this. So remember, here's our upper Darbo integral of f. And what we're saying is that if you take a refinement, you get closer to your upper integral. Okay, so here would be upper FQ, and then back here would be upper FP. Okay, because if we look at this same picture, and now suppose we were to look at the supremum, well, let's see here. So now the supremum over this entire interval times the width of the interval would be this. So this is an overestimate of the integral, right? It's an overestimate. We're estimating the entire function by the supremum of the function, overestimate. Our overestimate will get better if we are allowed to have a finer partition. Okay, so now I would just have from here to here and from here to here. Right, so you see now my overestimate is getting better. Right, so the finer my partition is, the closer my sums are to the integrals. If my lower sum and my upper sum are equal to each other, then my function is integrable. Okay. So we can go back here to this function, to this inequality that we proved. So we proved this theorem, or this fact, all the way at the very beginning. This was one of the first things that we did, right? And here's why I'm bringing it up again, is because notice that little m times b minus a, this is just what you could call the laziest partition ever, right? So this is the Riemann, not the Riemann sum, this is the Darbo. So this is LFP, the Darbo, lower Darbo sum, when your partition is just AB, right? And this one is your upper Darbo sum for when your partition P is just A comma B, right? So if you don't even really partition, you just say, here's A to B, give me my, take the supremum of the function, take the infimum, right? That gives you these this lower estimate here is using the infimum of the function over the entire interval, and using the supremum gives you the upper estimate. So if we know, right, if we know that refinements get our sums closer to the integrals, then any p is going to be a refinement of just this very basic partition here of just a and b, right? Because any p has to have t naught, t1, all the way up to t sub n, and t naught has to be a, tn has to be b, right? So any partition is going to be a subset of just ab. So any partition is going to be a refinement of this very crude, this is the crudest partition ever. Okay. It's pretty funny, I think. All right. Okay, so we've got another fact. Here we go. This fact is saying that if your function is bounded, then it really doesn't matter between P and Q. Any lower sum is going to be less than or equal to any upper sum. So with this, we're able to say that, what do we have? So we've got, if every lower sum is less than every upper sum, then you can imagine that this is going to imply that your lower integral has to be less than or equal to your upper integral, right? Because could you really have your upper integral bigger than your lower integral? No, you couldn't, because look, so remember your lower, this is the supremum of all lower sums. So that means we've got to have some lower sums that are getting really close to it, right? So this is going to be a lower sum, LFP, really close to L of F. And then similarly, since this is the infimum of all upper sums, that means that we better have some upper sums that are getting close to it. So this would be an upper sum really close to, which would be UFQ, really close to U of F. But now, according to this fact right here, every lower sum is less than or equal to every upper sum, so you can't have it, right? You can't have this. You cannot have an upper sum that's really close to U of F and a lower sum that's really close to L of F, and the lower integral, the lower sum is bigger than the upper sum. Okay, so let's see why add a page below. Y is any lower sum less than or equal to any upper sum. And this is for all partitions P and for all partitions Q. Okay, so here's the answer. And the answer is really short and really cute once we use our fact about refinements. So basically, here's what we do. So we say if, so we'll say let's see here. Let's do a formal hypothesis is that f from A to B to R is bounded. So f is bounded. P and Q are partitions of AB. The claim is that the lower sum with respect to P is less than or equal to the upper sum with respect to Q. And here's the proof. All right, so here's what we're going to do. We're going to say that let's see here. So P union Q is a refinement of both P and Q, right? Since P is going to be a subset of P union Q and Q is going to be a subset of P union Q. So that means, so now let's think about this. So if here's our lower sum with P, the lower sum with P union Q is going to be better than the lower sum with respect to P. And the lower sum with respect to P union Q is going to be less than or equal to the upper sum with respect to P union Q. And that is going to be better than a better approximation of the integral than the upper sum of F Q. All right. So for the proof, so we'll just say, since P union Q is a refinement of both P and Q, we have that the lower of FP is less than or equal to the lower of FP union Q, and the upper of FP union Q is less than or equal to the upper sum of F with respect to Q. Finally, lower sum of FP union Q is less than or equal to the upper sum of FP union Q. So the result follows. Okay, because remember, you always have, right, for any partition, the lower sum with respect to that partition is going to be less than or equal to the upper sum, because that's going to have the infimum of the F, and that's going to have the supremum of the F's, right? Times the delta T, sum. Okay? All right, so we proved that. Now let's prove over here that always that the lower integral is less than or equal to the upper integral. And we kind of already saw in a justification for that. But let's go ahead and write it out all the way. So if we have hypothesis is that F from AB to R is bounded, that's hypothesis. And the claim is that the lower Darboux integral is always less than or equal to the upper Darboux integral. That's the claim. And now for the proof, I think we should try to do a proof by contradiction. So by contradiction, we would say suppose not. That means that the upper integral is strictly bigger than the lower integral, right? So if we let epsilon equal, all right, miswrote this. That means that the lower integral is bigger than the upper integral. And we'll say let epsilon equal the difference. Okay, so then epsilon is greater than 0. And since the lower integral is equal to the supremum of the set of lower sums, there exists a partition P such that, so here we are with the picture here. So there has to exist a partition P, this is epsilon over 2, where LFP is within epsilon 2 of L of F. So we'll say such that LFP
It's 19:15.
is in between L of F and L of F minus epsilon over 2. Okay. Similarly, there exists a Q such that, we're going to say there has to be a Q over here. So the upper partition, the upper sum with respect to Q is going to be in between U of F and U of F plus epsilon. So U of FQ is less than U of F plus epsilon over 2 and U of F. Okay. So the difference between, okay, so here, what do we want to say? We want to say, so if U of F is here, U of F plus epsilon over 2, because we said epsilon over 2 is, epsilon is L of F minus U of F. So this is going to be equal to L of F minus epsilon over 2, which is less than L of FP. That's an L of F, right? So the key problem here is that we've got U of FQ less than L of FP. This contradicts the fact that lower sums are always less than or equal to upper sums. Okay. So U of FQ is less than L of FP. Contradiction to our last fact. Okay. So this is getting into Riemann sums. Where's our definition of Darbo integrable? Oh, we already gave our definition of Darbo integrable. Okay. So we're done with proving facts. You see kind of how to manipulate your lower Darbo sums, your lower integral, upper sum, upper integral. With this last theorem, we know exactly how Darbo sums and Darbo integrals look. So this will be the upper integral. This will be our lower integral, lower Darbo integral. This is our upper Darbo integral. And the upper Darbo integral is the infimum of the all upper Darbo sums. Okay, and the lower Darbo integral is the supremum of all lower Darbo sums. Okay, and so F is Darbo integrable if and only if the lower Darbo integral is equal to the upper Darbo integral. Does that make sense? Which is the same thing as saying that for every epsilon, you can get, right? So if this is your upper and it's equal to your lower, for any epsilon, you can have some lower sums that are within epsilon of u of f. And you can have some upper sums that are really close to L of f. Okay? All right. So now let us get back to the definition of a Riemann sum. So Riemann sum is something that hopefully you've seen before in calculus. It is similar to a Darbo sum, except Darbo sums use infimums and supremums, and a Riemann sum is using an actual value of f at some point in that subinterval. So Riemann sums is you are sampling f. On the subinterval t sub k minus 1 to t sub k. Okay. So one thing to note is that you have infinitely many Riemann sums associated with any partition, right? So there are infinitely many Riemann sums associated with any partition P of F. So this is a big difference between Darbo sums and Riemann sums. For Darbo sum, you only have one Darbo sum. You only have one upper and one lower, right? But for Riemann sums, you've got infinitely many associated with each partition. Okay. The next thing we need to know about is the definition of the mesh of a partition. And basically the mesh is just the maximum length of the subintervals comprising P. So a mesh gives you an upper bound on an upper estimate on how wide your subintervals are. Does that make sense? So it's kind of like if you have a colander and want to know what's the mesh. Well, the mesh is going to be based on the biggest hole, right? What's the biggest hole in your colander? Okay, and it's the same thing here. So the mesh of your partition is determined by the maximum of the lengths of the subintervals. And here's our theorem. So our theorem says that a function f is integrable, Darbo integrable, if and only if for every epsilon there exists a delta such that for any partition whose mesh is less than delta, the difference between the upper and the lower is less than epsilon. So now notice that this implication here is saying that u of fp is going to be less than the lower Darbo sum plus epsilon. So what we're saying is that your function is integrable which means, right, so f is integrable if and only if the lower Darboux integral is equal to the upper Darboux integral, right? And we're saying that if that happens, then your upper sums, which are over here, you can make it so that your upper sums, for each upper sum, it's actually less than epsilon plus the corresponding lower sum over here, right? So the textbook calls this a Cauchy criterion, for integrability, because it's kind of like you're taking a worst case scenario and you're saying that any partition that has a small enough mesh will satisfy this property for its upper and lower sums. So I will leave you to look at, the proof is not that bad, on page 275. So this is actually theorem 32.7. So I will leave you to read that proof in the book. And now, we already gave the definition of a Riemann sum, sorry. So we talked about how here you're just sampling your function, and there are infinitely many Riemann sums associated with each partition and each function. Now we'll give the definition of being Riemann integrable. So you're Riemann integrable if there is a number r, a real number, such that for every epsilon, there exists a delta where for every Riemann sum, if the mesh is less than delta, then the sum minus r is less than epsilon. So this is similar to the Cauchy criterion for Darboux integrability. Okay, and then the number r, that number is called our Riemann integral, and we write it like this. So you'll notice that it's the same notation because we have this theorem here, which is a major theorem, and this is 32.9. Again, I'm going to leave it to you, page 32, theorem 32.9. I'm going to leave the proof of this for you to read. It should be doable. It's a doable proof, so I'm going to leave it for you to read. And you're saying basically that a function is Riemann integrable if and only if it is Darboux integrable, right? And if they are, right, if a function is integrable, then this value of r is the same as your upper Darboux sum and your lower Darboux sum, okay? All right, so that is it for section 34. I know this was a long one, so I'm kind of trying to hurry it up at the end there.